Hi, everyone. Welcome back to the Weighty Thoughts podcast. I guess we can call it a podcast at this point. We've done enough of them, I guess. Regardless, it's another one of the interview in the series of interviews that I've done in the course of research for my book, What You Need to Know About AI, which is coming out this fall. That's just a few months away, so definitely watch out for interesting and new book updates as they come up. Anyway, today we have Brandon Basso. He's the director of simulation at Cruise, which is one of the self-driving car companies now acquired by GM. He was previously at Uber ATG, the Uber self-driving car initiative, and he's been in the industry for quite a while at this point. He's got a lot of interesting perspective on, obviously, self-driving cars, but also different topics within AI, simulation, autonomy. Anyway, I think today's interview is really interesting and hope you enjoy.
Great. It is awesome to have you, Brandon. It's been a while. And I think it'd be great to just start out with some of your background and history, especially since you have such a fascinating one with both drones and self-driving cars.
Yeah, absolutely. Well, thanks so much, James, for having me. It's a thrill to be here. Going back to where actually you and I met in grad school, I was working as part of this group called the Vehicle Dynamics Lab and doing a bunch of different projects having to do with unmanned aerial vehicles and controlling groups of them. And at that time, it was interesting. There was a bunch of people that were working on cars and autonomous cars as well. And they were not the popular ones. They were the ones that kind of were off on the side. And lo and behold, those were the ones that ended up building the industry that I work in today. But yeah, where I started out, it was all in the drone space. I did my PhD in Berkeley, at Berkeley, focusing on applying machine learning techniques to solving problems like routing problems for routing groups of vehicles like drones. Tons of fun. Ended up actually using quite a bit of that to go work at 3D Robotics and actually go get to build enterprise and consumer drones. Leveraged a lot of background in control theory and estimation and stuff that I also worked on. And then after that, this is when the autonomous vehicle industry was starting to pick up. I moved over to Uber ATG and then later Cruise, where I'm at today, where I'm in charge of simulation and evaluation for the autonomous vehicle. I think this is one of the hardest last frontier challenges for autonomous driving and for AI in general. How do you evaluate if it's good or correct or safe or what those things even mean? In the first place, how do you do it at scale? And how do you do it when you're shipping a production software system to the road? And that's the parallels with the current Gen AI universe. And then the only difference is that what the car does has a real tangible, real world impact, unlike a string of text, which has some impact, but this is very very visceral, of course. So that means that you have to be really sure about your evaluation.
Yeah, and that's all stuff that I want to jump into quite soon, actually. But before even going there, just how did you personally get interested in this kind of stuff? Was it you were always interested in drones, cars? Like, how did you get into it when you were younger?
Oh yeah, gosh. I mean, I'm the son of an engineer, so I'm sure that had something to do with it, at least maybe genetically. But it was really in undergrad. I was at Columbia in early 2000s, and I took my first controls class there, and I was just absolutely fascinated by the concept that you could use math to prove how a real physical system might work or might react, and these concepts of stability and convergence and how they had these real tangible impacts. And I remember taking a mechatronics class where you did sort of a classic mechatronics-y thing where you floated a ball bearing and, wrote the microcontroller for it. And just that connection of math to the real world was just super fascinating for me. So from there, it was on to, whatever vehicle, whatever robot I could get my hands on to go work on and control. I did a really cool senior design project. I was part of a lot of mechanical engineering curriculum at the time, building a small robotic water strider, one of those little bugs that sits on the water, and both machining it by hand and then working on the little control system that moved it around. It was a super lightweight robot too, which was cool. So really, I was just drawn to this concept of using math to both measure the real world and then also react to it. From that moment on, I just wanted to be involved in every possible robotics project I could be.
Yeah, and it makes a lot of sense. It is a cool area. I'm glad the world as a whole is starting to recognize more that it's a cool area. But I mean, speaking of the things that you were saying for early on within the industry, I mean, the DARPA Grand Challenge was a long time ago. A lot of the different self-driving car stuff, we've had it for a long time. I guess you were alluding to it just in terms of how tough a lot of these different problems are. Why don't we have more self-driving cars around at this point? We've had this kind of concept and everything for years.
To me, it's important to note where we sit in time, the very beginning of 2025 and what is the present state of technology. And I think that we're at this very interesting inflection point where anyone who lives in San Francisco, it's impossible to not see some of the cars being driven around, and especially the amazing progress companies like Waymo have made recently, but also Tesla and the amazing scale that they operate at with full self-driving. So yes, it's taken a long time to get here, and yes, there's still a far ways to go. And I can get into what I think the challenges are there in a second. But it's important to note that today, I can go walk outside my office and get in a self-driving car and take it to basically wherever, and it will work exactly like an Uber in many ways. So that's a huge testament to, I think, everyone who worked in the industry going on back to the original DARPA Grand Challenge people. I think there were several unlocks in the industry that got us to where we're at today. For sure, early on, a big unlock was hardware and sensing hardware in particular. Now, most of these cars, even today, are incredibly expensive because the hardware is bespoke, the computers are bespoke, the sensors are bespoke, and those costs can and should come down over time. And OEMs like Tesla have already done a lot to bring the hardware costs down. But I think that's one big thing that changed, was just at any cost, capable hardware, LiDARs, radars, and cameras. And that can't quite name the exact year, but at some point became more commoditized and more able to buy it from tier one suppliers. And if you were to start a self-driving car company from today, autonomous vehicle company, you'd probably buy the vast majority of compute hardware and sensing hardware off the shelf, which is very different than how it was when I started in the industry, and especially very different from the DARPA Grand Challenge days where almost everything was completely bespoke. So hardware was a big unlock. And obviously another big unlock was just AI, early on computer vision, but deep learning techniques and moving away from rules-based systems. I think what a lot of companies found was that their rules-based systems worked well up to a point, but this interesting thing happens where you drive more and more and you push those systems to their limit, and because they're performing better and better and better, you see less examples. And because you see less examples, you have less feedback, like in a control sense about like what you can improve upon. And then it gets harder and harder to drive improvements into the system because you just don't have as dense examples. And what machine learning really unlocked for the industry was the ability to directly connect the data into the improvements of the fleet. Of course, this involved driving those fleets at massive scale. So companies like Tesla have a huge advantage here where they can go collect large amounts of data and drive those improvements directly back into the system. But that was another big unlock. This is, really glossing over tons of other achievements that happened in really, boring stuff like dev tools and build systems and all these things. And the amazing thing about self-driving car companies is there are these research labs where you're really doing cutting edge research, but you're gluing that together with a actual production software system that's shipping code, weekly or bi-weekly to the road. And that just requires a massive amount of infrastructure and stuff to work. And, some of the most impressive stuff that I find in the industry and at Cruise is just kind of the basics of just like dev tools and build systems and software frameworks. I think all that stuff was hugely important too. And maybe not as forefront as the stuff driving the car, but nonetheless important.
Yeah, totally. I mean, there's always tons and tons of layers to this kind of stuff. And I think the thing that you mentioned for rules-based systems and symbolic systems and some of these other systems that were more in vogue during the 80s and 90s, giving way to a lot of this deep learning techniques, that was in the industry more broadly as well, right? Just because the issue of variation is such a big one where most rules-based systems will eventually run into a big serious issue in the real world because the real world isn't quite as neat. But we also have the other pushback in terms of that where some of these systems are often a black box. It's like a question of like, can you audit these kinds of things? Can you actually understand like what these things are doing? Because who knows, there may be an edge case that's within the system that's hard for you to actually catch. On the other side, just to throw this in, there's been recently a big movement among different folks online where they're basically all pointing out these self-driving cars have better rates of, not having accidents and these other things than human drivers. So actually the issue is too much safety regulation. So I've been seeing both kinds of arguments go out there. It's like it's deep learning, it's a black box. We can never know how truly safe it is. And this is a more dangerous area than, say, a Netflix recommendation or a chat thing. But at the same time, it's so much safer than humans. Maybe regulation's just getting in the way. I guess just throwing those two contrasting points out, like what's your opinion and thoughts on that?
Yeah. So they're really two different points that I think are sometimes conflated wrongly in the tech media, but they're related for sure. So, one concept is, how can you verify an AI system, a system of systems, like a system of models, or even an end-to-end system? How can you prove any properties about that? And then two is, what is the safety of the end product at the end of the day from a metrics or an evaluation point of view? And I think about both those problems a lot because, at least half my job here is evaluation. And, the first question, it's not necessarily the case at all, or I don't agree with it, that you can't evaluate. There's anyone who works on ML models know that you can use all sorts of rich tools to see what is happening exactly with the weights of each weight in a network. And even for an end-to-end model, you can still design it in such a way that you can introspect into it and measure certain things. Now, what those signals are might not have as tangible of a understanding as like the internals of an analytical control system, where you can directly measure this thing and know that it is the Kalman gain on this number, so on and so forth. But I don't think that just because AI systems and neural networks are complex, it doesn't mean that you can't evaluate them. You still can, and some of the best practitioners in the world do that, in fact, and use that to understand what's going on, especially if you're debugging why your training isn't working, or, do you have a data deficiency problem? So that's like one almost like myth level thing that I would like to debunk, which is like, you can't do thorough V and V, or however you want to put it, on a model. That's just not the case. I think there are very legitimate concerns about when you make a complex system, if you deploy it and just send it out to people without doing thorough evaluation, there could be problems, but that's not due to lack of evaluation techniques, in my view. That's just due to lack of rigor. And it is a hard problem, but it's not an unsolvable problem. So that's my bit on evaluation of models. On the safety of these systems, I think that, like I mentioned, Waymo and many other groups have published statistics on this. I think it's hard to deny that lots of these systems that are deployed, especially the current robotaxi fleets, are safer than humans on average. I think that that's very clear. That doesn't capture one key insight, though, which is people don't always care about just safety. What happens if your car, you're in a robot taxi and you're visually impaired and you pull over to a pullover spot and you can't get out for some reason because it's dangerous or because there's a big curb or something like that? No, that's a very hard problem to solve. And there's other cases like that where, it's not strictly about collisions, right? There's these other forms of safety, and even beyond safety, like comfort, that are safety adjacent, that are much harder to measure and assess. I think that it's my view as a user of the technology is, and my understanding of the statistics is, in many cases, they are better than average humans. The question is, what is the bar? Is it to produce an average human driver? My interpretation of that is no, absolutely not. It has to be clearly much better, let's say like 10x better than humans in a large set of circumstances. It has to have, and there has to be like really strong data to back that up. I think in other sets of circumstances, maybe you can get away with having a more loose bar where it's okay, or if it's excusable, if it does some things that aren't exactly intuitive, but they're not necessarily unsafe. And then I think that there's a whole nother class of issues that you just want the robot car to absolutely never do. And that's really the hard part. There's a set of things that I think most people would look at and call inexcusable, even if a human did it, or things that maybe a human would never do. And bucketizing the behavior into categories like that, I think, is a challenge. And that's really what companies are trying to do now, is just understand what are things that we need to do 10x better than humans. What about things that it's just okay to be as good as humans? And then what are the things that just can never happen at all? Yeah, that's I think where we're at with evaluation. But yeah, long story short, I think it's very tough to deny the performance of some of these systems. And I think that they're only going to get better as you add more data.
Yeah, makes a lot of sense. I mean, I guess going along one of those lines, because you were talking about safety and we're talking about regulation and everything, I think it's too simplistic a lens to just say too much, too little regulation. There's a lot of different dimensions to it, obviously. But I remember one of the things, which at this point definitely I can share because they're way past this, in terms of in Google X and talking to some of the what became Waymo people. Here's a big question. It's like if a car gets into an accident or other things or needs to choose sort of trolley problem kind of things, who takes the liability? Who has the sort of moral obligation around it? And how do you actually parse these things suddenly when it's not a human driver? How do you think about just the landscape right now of regulation and like legal or even just some of these moralistic questions around self-driving cars and what the state of it is right now?
Well, I have to say this is starting to get way far out of my domain. I think it's really important. So I'll just say some like basic like functional things. I think it's really important to work very closely with regulators in any city or town that these things are deployed in and view them as really a partner and a customer because they have their constituencies. They need to present data to their regulators or whomever, the mayor, the governor, and they're a customer essentially. And I think it's super important that they get treated as such as part of an overall landscape. It's not just about the person in the car taking the ride. It's about all the people outside and then all the people who need to make decisions about whether or not it's a good idea to deploy. So that's just like my baseline answer. I think that when it comes to questions like, gosh, I haven't heard the trolley problem question come up in quite a while, which I think is a good sign. I think it's a sign that we've moved past these sort of like semi-false binary choices because, the reality is the car is doing a decision-making process exactly like a human is in some sense. They're weighing a bunch of probabilities of outcomes, weighing its own response time understanding and making a choice. There's nothing moralistic about that. And a lot of it is just supported by data at the end of the day. Like what do human drivers do and how do they act in certain scenarios? The real difference with the robot car is twofold. One is it has a perfect understanding of its capabilities versus you and I as drivers, we have very imperfect understanding of that. Two is it has a perfect understanding of, given a situation, what is the maximum sort of braking force or acceleration or whatever it can apply. Whereas like you and I don't necessarily jab on the brakes at a 10G decel or whatever like that often. So there's a much better understanding of the system from the robot car test side. But does it make the right decision in the end of the day? I think that's a question for the insurance adjusters. Like I mentioned back in the evaluation side, one of the really big problems for evaluation is compartmentalizing into what can never happen from a regulator's point of view. This is why it matters to have close partnership with them. What is acceptable to happen at some error rate where we can define the error rate, and then what just has to be superhuman, like 10, 20, 100 times better. That's the contract that needs to exist. And from what I read in the news and what I've seen is regulators have been getting a lot more sophisticated about this line of thinking. And it's not no collisions anywhere ever. It's sort of thinking about it in these sorts of categories.
Great. And that makes a lot of sense in terms of it. And hopefully we keep getting a better societal understanding of what our relationship is with a lot of this AI stuff. But I guess in terms of thinking about this, right, you were talking about there's a lot of different hard problems within the self-driving car space. I think a lot of people underestimate it. I've not to caricature certain people, but certain like grad students come out and it's like, I did SLAM in my grad work. It seems like I should be able to just get a car going around San Francisco and have it be able to figure it out. What's so difficult about that, right? So what are the really big challenges in terms of deploying these systems to the real world that you encounter in terms of self-driving cars in this area?
Yeah. So one challenge I think about all the time, like I mentioned before, is evaluation. So is working on an autonomy system very hard architecturally from a modeling perspective, from a data perspective? Absolutely. Super hard. I worked in that area for a while. Huge advancements happening in that space is a very hard problem. That said, I think that as we're starting to see these systems really, really hockey stick in terms of their performance in a variety of road conditions, a variety of cases. One problem that seems to me that is just still very challenging is how do we understand what is good for these systems? And how do we measure that at incredibly high fidelity offline? Because having incidents in the real world is expensive and problematic. And both of those are super hard challenges. So Getting it right, I think, comes down to a couple of key things. One is, do you have the right data in your test set? Do you have the right coverage is one way to put it. Measuring coverage is a science topic, but you need to understand what data you have in your test set, your evaluation set, and what you don't. Where you don't have the right data, you need to go generate that data from scratch. And that's one of the big missions of simulation teams is generating those examples to evaluate against. Once you start generating simulation examples, you bring in a whole host of questions about the validity or the fidelity or the realism of those examples. And that's a whole other science question to go answer. Once you have the examples, you need to be able to score them. And that's essentially the job of validation. And it needs to be, I think this is actually subtly one of the hardest parts. It needs to be at a high enough signal to noise that you can show it to a developer at the speed that their development cycle works on, which is hourly, maybe daily, in a high enough signal way that they're not looking at a million different potential failures, but not really figuring out what's going on. And that's hugely challenging as well, because we've moved way past the point where you just have these static test cases that are like binary pass fail. Oh, did you hit this object or not? Like, yes, that's of course like part of it, but we're way beyond that now. And unless you can focus the developers, the people working on the autonomy stack, on the actual problems and contextualize them to other problems they're working on and explain in a way that makes sense about if you change this, it affects this and it affects that, and those sort of effects, then it's very hard to do development. So it's a development tool, it's a science, it's a huge challenge. So, if we solved evaluation, it's not that you would solve the autonomy problem, but you would make the autonomy problem and delivering better versions of the autonomy system to the road, you'd make it go 10, 100, 1,000 times faster.
Yeah, totally. And I think this also plays into sort of the other side of it, which is why you need so much evaluation, which is variation. So I've talked to a lot of different startups. I've looked at like lots of different things. One of the challenges for many of these different systems is you have the real world. For some of these, like, kitchen robots or whatever, way easier to do back of house than front of house. Why? Back of house, you have some control of it. You can create corridors, you can like have some sort of restrictions or whatever. Front of house, who knows? Like someone could wander in the way, some baby like gets loose and runs in front, like a dog is there or something like that. And, a very similar kind of environment is with self-driving cars, where all sorts of things could happen on the road. I mean, can you talk a little bit about the thought in terms of variation? How do you actually take all those things into account? Because we're talking about coverage, which again is sort of the other side of it in evaluating this, but yeah, how does variation play into this?
Yeah, variation is incredibly important because you only need to see one event in the real world once for it to be a huge problem. And maybe you never saw it before. And back to this improvement cycle, as cars get better and better, they're just going to see those events less and less. And the chance that you don't have that next problematic event in your data set just gets higher and higher. So it's this very interesting sort of effect. So how do you generate meaningful variation offline? The hard part of this challenge is, I'll tell you what's not hard. It's not hard to take a simulation system like the one that I work on and say, given a scenario of a car driving down a street and a pedestrian coming out of occlusion, generate dense sampling of 1 billion different variations of this scenario according to along the parameter space of the velocity of the pedestrian, the type of pedestrian, height, clothing, the time of day. You can very easily see how you can, very densely start to sample this parameter space. That's not the challenge. The challenge is, give me the 2 variations in that the car will actually fail or not do well. And how do you go discover those? So, one approach to that is actually just doing that evaluation in very tight closed loop fashion with the autonomy system as well as sort of like an RL style simulator. That's one way of doing it, where you just sort of like generate these billion examples and you simulate and you train you score and you train it all in the same loop. So that's one. There's more formal methods for exploring this parameter space and doing things like hazard analysis to discover where the challenges might be. And that might be an important thing to do from a regulatory perspective anywhere, where you can say definitively, I've covered the following cases. One really interesting way of doing this, I think, is start from an example that did happen in the real world that maybe was not problematic or problematic adjacent, and you want to ask a counterfactual about it. Well, what if the person popped out a little bit later Or can you perturb this scenario in a way that makes it harder for the AV to act correctly in? And that sort of perturbation approach, I think, is a nice little cheat code where you start from a scenario that you already know is plausible because it happened in the real world, and you ask the system to densely sample around it. So variations are incredibly important. It's not hard to generate a lot of them. It's just very hard to find the meaningful ones. And there's a couple different techniques that you can use. One technique that I think is not used enough is just looking at examples that are happening out there every single day from human-driven cars or other autonomous vehicles from other countries, whatever. Like there's so much driving happening in the world right now, and the data capture from that is, rounds to zero across every car that's on the road. So if there's some way of capturing that, I think that that's also a very useful signal.
Right. And that actually gets into two different topics. But the first one that I'd love to just get your thought on is there's been a lot of approaches to self-driving cars. There's been HD maps, there's LiDAR, there's just using RGB cameras, like, with Tesla and, well, they have some LiDAR and other stuff, but like Tesla and some of the like different approaches in terms of this. What do you think of a lot of those different sort of methods? Like, how do you think through the problem? Like, what is the appropriate, modality of sensing? Like, how do you actually work through some of those things?
Yeah, I think that all autonomous vehicle companies basically live in like a 2D grid in terms of their approaches. On one axis in the grid is capability, like very broadly speaking, and on the other axis is cost of system. And the bet of a company like Tesla is that they can start from a very, very inexpensive system and drive the capability up over time. And one key element to that approach is massive data capture and data scale. On the other end of the spectrum, you have companies making the opposite bet, which is that they can start from an extremely expensive system. This is more like the Robotaxi approach, and then cost it down over successive hardware iterations. And, I know that the media likes to contrast these two, especially, if someone comes out very strongly against a particular sensing modality, but that at the end of the day, it's just a cost and capability trade-off. I don't know why else you would frame it as anything other than that. What's the BOM cost you can afford to put it on a ton of vehicles where you get the huge data capture upside, but you have this downside of like limited capability versus let's start from the very expensive system, but know that we just can't make a business out of that until we reach certain cost efficiencies. These are ultimately business decisions. I think they're technology decisions. And, in the early days where we didn't have much data on this, I think, you just had to sort of make a bet, and you saw people making the Robotaxi bet and then other companies making the more style bet where you can just deploy this to a large fleet. I don't think the jury's out on this, right? Like you see Waymo and other companies investing huge amounts of money in their approach, and you also see, and doing incredibly well, and you also see Tesla and all sorts of competitors from China now investing in that style of approach and doing incredibly well as well. So I don't think that it's clear. It's not clear to me yet which of these works. So sorry, I'm sure that's a very unsatisfying question or dodge to the sensor question, but I think it's all like kind of wrapped up in this like capability versus cost trade-off.
No, I mean, that's perfect. I mean, looking at some of the stuff in the Substack and the book, a lot of topics end up going that direction in reality because you can come down really hard on one side or the other. And certain people who really like to tweet or X or whatever do come down very hard on one side versus the other. But yeah, I think the reality is messy in terms of that. But this gets to the second topic, which I think actually you're really well suited to address, which is simulation. Even a lot of the LLMs and frontier models are now using different RL type loops, simulation, synthetic data, and other things to help drive performance higher. But one of the questions that people have is like, how far can you take this method? How good is the synthetic data? And also just hearkening back to the Nature paper that talked about this, will you just get model collapse and slop everywhere if you could just keep going down this path?
Yeah, so I think you could take it really far, but also I have a vested interest in saying that. And I think you could take it. I think you can take it. I think you can take it incredibly far. I was actually just reading a paper, some advances of an RL simulation applied to autonomous cars. I don't think that we've seen the benefits of this technology yet on the road, but from what I've seen, I think there's a couple amazing things that can happen via using these techniques. One is you really speed up the developer loop, which just means you have more shots on goal to get it right. That's a very practical thing. Two is you're able to generalize from one set of behaviors that the car has to another set of behaviors in a whole variety of different methods and in a very robust way that's just not really a property of how the other systems work. And then the other property, not really specifically related to simulation, but worth mentioning, I think it's really interesting seeing what's happening with the research with working on large models that you can distill down to much smaller models that still happen to have incredibly high performance. And I think that's a really useful insight. And I imagine that type of insight is going to drive a lot of the work that's going to happen in the future where, maybe that large model never goes on the car, but future versions of it do, or you have just distilled versions of those that go on autonomous vehicles in the future. All of this stuff is predicated on having a simulator that can scale from this like very tight inner loop, super fast, maybe lower fidelity, but super fast rollout generation, all the way up to this more end-to-end style simulation where you're doing something more like validating against a bunch of, test cases or something like that. How you build those simulators is there's a million different ways to do it. I'm sort of implying that needs to be one simulator. That's not the case. You can build it in a variety of different ways, but it's at the point is that it's at the center of all these different development loops, the super rapid inner loop one, and then this all, sort of like outer loop end-to-end use case. So incredibly impactful technology for doing development versus just doing validation, which is maybe more what it was used for years ago.
And along that line, just another one of those things that kind of ended up in the middle. There used to be very strong opinions on whether or not centralized computing or edge computing would be more important and would take over most of the spaces in whether it's self-driving cars or a lot of other things. In reality, I feel like we've seen in a lot of industries much more of a hybrid. I guess, do you have any thoughts in terms of that and what the future is in terms of more centralized computing, more edge computing, some of these smaller distilled models locally? Like, how do you think through if someone were to ask you the question about what do you see going forward?
So you can't get around, ultimately you can't get around the fact that this is a real-time system. This is one of the paradigms I think that has held true over the past few years that hasn't changed with all the recent technology developments, which is if you're driving a car down the street and it ultimately needs to respond on the order of maybe tens of milliseconds, what is the comms link you're willing to put that over? I can't think of one from like a physics point of view that you're willing to put that over. Now, yeah, wouldn't it be great if you had some computer doing that in maybe some, distant universe? Yeah, that's possible due to some telecommunications technology I'm not aware of or hasn't been invented yet. But the other thing is like it's not like the cost of having the computer in the vehicle, the compute hardware in the vehicle. It's not like the cost of that is necessarily prohibitive. I.e. previous examples where we talked about Tesla. So I don't see there being a huge imperative to move much off-board other than the following. We already know that robotaxi companies, via lots of reporting, have heavily leaned into remote assistance systems. So what do those systems look like? It's the vehicle usually the autonomous system on the vehicle making a call to call a human, phone a friend, have the human tell it what to do. Well, why can't that human be some model? That's like one area where I think there could be centralized offboard compute used to help aid, and I'm sure that sort of thing is happening out there already. Why not? Show it a picture of a scene and say, where should I pull over? Something like that. I think that all that stuff has a lot of relevance going forward. That mostly, in my view, it makes the user experience better, but it really drives down operational cost for these companies where they spend a huge amount of money, remote operations.
Great. And maybe let's talk then about where you see some of the biggest misconceptions about self-driving cars. This is a little bit open, but lots of people have lots of opinions now, especially since it's much more available and people can see it. Where do you see something that's really just misunderstood about whether it's the difficulty, whether it's the whatever it is?
Yeah. I'll give you two. I don't know if they're misconceptions so much as they are, lack of understanding or awareness. So the one is that it's still a distant technology, and it just doesn't feel that way to me. Now, I think there's deployment challenges, but I don't know about your news feed, but I see every day a new launch or a new partnership with a new ride-hail company or a new city or something like that, and I think we are really in this hockey stick growth moment. Now, Is that a mirage? I don't think so. I don't think it is, based on my personal experience getting in the vehicle and seeing it. So I think it really is. Yeah, not many people are getting in them today. Like, relatively speaking, it's a bunch of people in San Francisco and a couple other cities, but I think that's going to change really, really soon. So that's like sort of maybe lack of understanding just due to like geographies of where these things are. Number one, thing one. The second is, and this was probably my biggest misconception, honestly, before I got in these cars. And I worked at Uber for a while. Great company. I love the product and love what it did and how it works, and all the ride hail products. I think they're hugely transformative. That said, there are downsides to getting into an Uber with a person. And I think Uber works very hard and Lyft works very hard to limit those downsides. But the thing that struck me most about getting in my first autonomous vehicle ride in San Francisco was just how relaxing it was and how much I truly enjoyed it. And internally, we had all these concerns about things like, and we had all sorts of metrics around, well, how much longer is it going to take? Because you can't route in exactly the way a human would, or, longer because you're following the speed limit, or a variety of other things. And in more circumstances than I think people realize, you'll be perfectly okay with some of the cons of a self-driving car, like that it predominantly won't break the law, where it will drive slower and more deliberately and maybe take a little bit more time. I think people are going to be completely okay with those because of how much peace of mind it gives you to be in the backseat of something that drives so confidently and so safely, and where you just don't have to interact with another person. I don't know about you, James, but when I go home at the end of the day or go out with friends, maybe this is just more a product of having 2 kids now, I don't want to talk to anyone. I just don't. I want to sit in the back of the car and zone out, and I want it to not be jerky so I can look at my phone and not feel sick. And, this is really to take nothing away from the amazing work of Uber and Lyft. I really want to be clear. I think that stuff's awesome, and I am a huge user and fan of those products, but there is something very special and non-intuitive about getting in a car that doesn't have a driver. And I think that once people experience it, are really, really gonna like it.
Yeah, it makes sense. And I've heard actually a similar sort of thing over and over again from different friends who have come in from out of town, get in a Waymo, and it's like, wow, I don't need to worry about anything. I just chill out and don't need to say hi. Don't need to worry that, I don't know. It's like, don't need which is fascinating in terms of that sort of human dynamic. But I guess more than any other industry that I've done these interviews or talked to, it seems like once these things get off the ground in a really big way, it would actually, take away a lot of the, Uber drivers, Lyft drivers, like taxi drivers' jobs in this particular case. I think most cases I've talked to, whether it's for lawyers or for doctors or for other things, it's definitely not the case. It's a productivity tool. Even in the case of one of my companies that I'm on the board of, which does pizza making robots, doesn't actually take anyone's jobs because there's too few people already, and there's only one person in a Domino's that was supposed to have 3. But in this case, it does really seem like it's going to take away jobs. Like, what's sort of your impression of it, and what's sort of your thought process on it?
I agree with Dara's point of view on this. Dara's CEO of Uber, I think he is obviously careful around this question, but he says, yeah, but not anytime soon. And, it'll happen in specific cities. And we already know that like a meaningful portion of the ride hail market in San Francisco is getting disrupted by autonomous cars. I think we also know that there's a kind of, I wouldn't call it insatiable demand for transportation, but there's certainly a high demand for transportation in cities. So, will it over time? Yeah. And it'll be slow though. It'll happen in certain cities. I think it will also open up new markets that are hard to imagine. It was impossible to imagine Uber existing prior to the iPhone existing. It will be impossible to imagine some industries that start up as a result of self-driving cars that you couldn't have before self-driving cars. And those are just brand new revenue streams that maybe don't affect as much as we're imagining the human-driven Ubers. These are all just hypotheses, and who knows? Of course, I totally get and of course empathize with the fact that this has the potential to disrupt people's livelihoods. And yeah, I think it's, you have to be honest about the fact that it probably will in some cases. But what's missed in that is, well, what new markets get opened up?
Totally. And the funny thing here is I remember seeing a lot of the case studies, especially since I had worked in Africa and other places where, there wasn't the traditional telecom networks. There wasn't all the landlines and everything that got laid everywhere. And they just sort of leapfrogged to cell towers. maybe the hidden silver lining of the US being this bad at doing transit systems is eventually, once we actually have more autonomous vehicles, we can just leapfrog and not need to worry about the fact that our transit kind of sucks.
That's right. No bullet trains or high capacity buses for us. We're just going straight to autonomous cars and maybe time machines after that.
Maybe, yeah. Totally.
Maybe, yeah.
So, yeah. But yeah, I guess just sort of finishing up in terms of some of this, what are you excited for about the future? I mean, whether here in terms of self-driving cars or just in general with AI or anything else, like, yeah, what are you excited for coming up?
I meant for self-driving cars enough, so I won't bore you with any more of that. I think like a lot of people, I'm really excited about the current AI technologies and their chance of real positive impact in our lives. And the whole concept of self-driving cars initially was that it would, of course, be safer, but give us time and space back. And I think that automation in general can do that. And I'm really excited about some of that for the new AI techniques that are coming out. And I think about myself personally as just a manager, how my job might change and might be better or different over time using some of these tools. So I'm not worried about the fact that, maybe it's going to reduce jobs or something like that. Of course, that's possible, but I think about how it might transform some of those jobs so that we can focus on different kinds of tasks or higher order tasks. And I got to say, I'm really recently very interested in these models for things in spaces like drug discovery. I think that stuff is fascinating. I think it's really relevant on our life sort of timescale. I think it's not too different of a problem from self-driving cars when you look at the shape of it, just with regulatory questions as well. Obviously, you need to tread very carefully with anything related to drugs and people and clinical trials and all that. But there's just a ton of promising research there too. So yeah, at the end of the day, you have these big industries. Transportation's one of them, healthcare is one of them, energy is one of them, food and agriculture is one of them. And, probably most places that I want to spend my time and my energy is working on one of those that has like a real tangible benefit for humanity. And I really like the promise of what these current AI techniques can have in all those industries, but especially healthcare.
Yeah. And I'm really excited for, especially if you can, or other folks, bring in simulation techniques. Because that is one of the big challenges I know for drug discovery and healthcare in particular. Getting good and reliable data, of which is quite scarce. So really excited about some of those things too. And really loved having you on this podcast, book talk, etc. And thank you so much, Brandon.
Awesome. Thanks, James. It was great to be on.
All right. Thanks, everyone, for listening. And a big thanks to Brandon for doing the interview. That's it for now. Like I said at the beginning, keep looking out for book updates. And in the meantime, stay tuned to Weighty Thoughts. I'll continue to have different content on AI there. Thanks, everyone. Take care.